Start finishing up. We're going to move into the chapter on Jupiter, but a little bit to finish up on Mars. Okay, so just to remind you, the next exam, again, 3 is on the 21st. Is 12, right? Yeah. So it's a week from Thursday. Okay, so we just wanted to review a little bit about what we talked about regarding Mars, and then we haven't really finished talking about Mars' atmosphere. So we're going to do that before we move on to Jupiter. Right now, I mentioned that Mars underwent a period of tectonic activity around 3 billion years ago, when the molten Mars actually did have convection occurring in its mantle, as you see here. So the point is that there was sort of an abortive attempt to create an ongoing tectonic process, which we have on the Earth, for instance, ongoing tectonic process. But it fizzled out on Mars due to rapid cooling, combined with an absence of radioactive decay elements, which would have been able to keep the interior molten a little bit longer. So what we see is the formation of the Tharsis bulge, upon which we see the Mariner Valley down here, which is a tectonic crack. And we also see the large volcano that we talked about before. Actually, I was planning to upload a photo of a pie my daughter made last night, because it also shows tectonic crack there. The pumpkin pie is a big crack right down the middle. It's sort of a thermal effect occurring in the pie, but I actually forgot to upload it. It's on my iPhone. If you really want to see the pie crack, right down there. But basically, that's what we're seeing here, is a fracture caused by upwelling due to convection. And this is a gigantic feature. It's actually about 3,000 kilometers long. It's actually stretched all the way across the U.S., 600 kilometers wide. So we sort of think of it as kind of a super Grand Canyon, but that's a little misleading because the formation process is actually completely different from the Grand Canyon. The Grand Canyon on Earth, of course, is a water erosion feature due to the Colorado River moving through there for millions of years. So what we're seeing is this, again, this very large tectonic crack feature on the Tharsis bulge, which is also the region of Mars where we have these volcanoes we talked about last time. Now, having said that this feature is tectonic, nonetheless, you actually see some sub-features that are due to water erosion, because there was liquid water in that area as well on Mars at some points in the past. But the overall feature that we see there is a tectonic feature, not a water erosion feature. Okay, so we talked a little bit about this flood that took place from the southern hemisphere to the northern hemisphere. So I'm just showing this global topology map, because you can see that the redder elevations are higher elevations, 4,000 meters above the mean. And so we see this kind of odd thing about Mars, that the southern hemisphere generally has an altitude, actual altitude that's 3 kilometers higher than the northern hemisphere. So as we'll see, that actually plays a role in this huge flood that took place from the southern hemisphere to the northern hemisphere. And it also is connected with the formation of the Tharsis bulge and the presence of the shield volcanoes. I showed you a photo of Olympus Mons already. It's truly enormous volcano. It's an extinct volcano. It's been extinct for billions of years. But at its peak, it was probably the most active volcano in the solar system. With a base 700 kilometers across, about the size of, there we go. I'll probably create the state of some drive application next year anyway. But about the size of Texas, okay, and about 3 times taller than Mount Everest. So an incredible feature that we're talking about. And it is a shield volcano, which means it's sitting on top of a hot spot, which is a point in the crust where we have a weak enough area that magma can actually punch through. That's also indicative of the Hawaiian island chain. The Hawaiian archipelago is actually also sitting on a weak point in the crust, but because the crust is actually moving as well, we actually get multiple formations of volcanic islands. So this is a photo from orbit of Olympus Mons, and you can see it's, I mean, you sort of can get a sense that this is a huge object, because for one thing, it has multiple calderas, which are the areas where explosions have taken place in the past. And so that gives you a sense that it's a very broad feature. Most earthly volcanoes are sort of, single caldera volcanoes, but this has multiple calderas. And you can also see that it actually extends above the frost line, so it's truly extending out, much higher up than any earthly volcanoes do. But it is extinct currently. It was active during the same period of time when the Garces Bulge was forming, when we actually had that convective activity taking place inside Mars. Okay, now seasons on Mars, you may recall that there's two things about Mars that are quite similar to the Earth. One is the tilt of the axis is about 24 degrees, very close to Earth's axis tilt. And remember, Earth's axis tilt is responsible for Earth's seasons, right? The tilt of Earth's axis actually drives Earth's seasons. That changes how high above the horizon the sun rises during the time of the year. So Mars is going to have seasons that bear some kind of resemblance to Earth's seasons, because that's a similar tilt of its axis. And for that matter, Mars also rotates about every 24 hours, so its spin is similar to Earth. So those two facts kind of lead you to believe that there's a pretty strong analogy with Earth. But there's one complication that comes into play with Mars, which is a little different than the Earth example, and that's that Mars actually has a significant eccentricity to its orbit. It's a larger eccentricity than the eccentricity of Earth's orbit. And remember, zero eccentricity is a perfectly circular orbit. So more eccentricity means more oval-shaped orbit, and that then means that there's a larger contrast between the perihelion distance of Mars, closest approach, and aphelion distance, farthest approach. Okay, so that's going to cause variations in the amount of solar heating. Now, if you combine the variation in distance from the sun with the fact that you already have a seasonal variation, just because of the tilt of the axis, if you piece this together, what it actually means is that one of Mars's hemispheres is going to have more extreme seasons, and the other one is going to have moderated seasons, because these effects I'm talking about, the change in distance combined with the tilt of the axis, are going to amplify each other in one of the hemispheres, and they're going to kind of partially mitigate each other in the other hemisphere. So we're going to talk about that now. Seasons on Mars. Well, we're already getting through here. Mars is farther from the sun during winter in the southern hemisphere. This is winter in the southern hemisphere because you see the south pole is facing away from the sun. So if you're down here in the southern hemisphere at this time, you are not going to see the sun rise very far above your horizon. So that's winter. Right? So what we've got plotted right now is Mars is in the position in its orbit, which would be winter in the southern hemisphere. But notice that that is also when the sun is farther, Mars is farther from the sun. So the southern hemisphere winter is going to be a really deep freeze. And then if we think about what happens on the other side, if we want winter in the southern hemisphere, that would occur when Mars is on the other side of the orbit, because then the northern hemisphere will be facing away from the sun, just like this. So this would be northern hemisphere winter, because we have the northern pole facing away from the sun. So if we're in the northern hemisphere, we're going to see a sun not rising very far above the horizon. So that's winter in the northern hemisphere. But notice that it happens to occur perihelion. So the winter in the northern hemisphere is partly mitigated by the fact that Mars is closer to the sun. So that kind of creates offsetting effects. You still get winter in the northern hemisphere, but it's not as severe as winter in the southern hemisphere, because that occurs on the other side. And then if you think about this and piece this together, we actually are going to have, also the strongest summer, right? And that's summer in the southern hemisphere right here. So that's summer in the southern hemisphere. And summer in the southern hemisphere occurs when Mars is closest to the sun. So you get an extreme summer heating in the southern hemisphere. Now this configuration we started with, this is winter in the southern hemisphere, but it's actually summer in the northern hemisphere. But it's occurring when Mars is farther from the sun, so it weakens your solar heating in the north during the northern summer. So the bottom line here is that these two effects combine together to give you extreme seasonal variations in the south and moderate seasonal variations in the north, because the two effects add together, if you think about the southern hemisphere, but they mitigate each other somewhat in the northern hemisphere. Okay, so again, just summarizing this here, Mars is farthest from the sun during winter in the south, so that's going to create the deep freeze in the south. It's closest to the sun during summer in the south, so it creates a warmer summer. And it's the opposite in the northern hemisphere, so we get extreme seasons in the south and more mild seasonal variations in the north. And this is going to actually also have an impact on Mars's weather patterns, because weather patterns are typically driven by planetary scale convection from the equator to the polar regions, and so as you would expect, that's affected by the variation in solar heating. Okay, so here we're looking at kind of a composite of the north polar cap, and we are seeing some seasonal variations even in the northern polar cap. And again, the seasonal variations in the north are actually less extreme than in the south. But we do nonetheless see seasonal variations in the polar cap cover. And so what we're really seeing here pretty much is variation in the amount of carbon dioxide, also water vapor at the polar caps, but it's mostly carbon dioxide variation that we're seeing in this particular set of photos. And the reason I say that is because carbon dioxide freezes at a lower temperature. So, we get snow around here, normal H2O type snow. We don't get carbon dioxide snow on Earth, because it really doesn't get anywhere near cold enough on Earth to freeze carbon dioxide out. But the polar regions on Mars actually are a combination of carbon dioxide that's frozen, what we call dry ice, and water that's frozen. So the thing that's going to vary first here is going to be the carbon dioxide, and then the water is generally going to be more frozen because it's able to stay frozen at a higher temperature. But anyway, we were clearly seeing seasonal variations there. Okay, so when we see variations in the poles, like I was just talking about carbon dioxide, well, if they're able to thaw carbon dioxide, now carbon dioxide doesn't exist in any liquid form on Mars. It turns out with the very low pressure that we have on Mars, what actually happens is the carbon dioxide, when it melts out of the polar regions, it sublimates. If you remember what that is, it sublimates. It goes straight from the frozen state to the gas state. So that variation we saw in the polar amount of carbon dioxide